Welcome to another IoT Central workshop. Please send any questions you might have in the chat. We will follow up with any unanswered questions using the email address you registered with. My name is Shawn Hymel. I'm a developer relations engineer at Edge Impulse, and today we're going to be talking about deploying a machine learning model, something you've trained on Edge Impulse, to any target using the C++ library. And there's a bit of a caveat because it's not any target, it's really any platform you have a C++ compiler for and enough RAM and flash memory to run your model. Edge Impulse is the world's leading embedded machine learning platform. It helps you build a full end-to-end machine learning pipeline to accomplish a variety of machine learning tasks, from regression to vibration and sound classification to object detection and predictive maintenance. You can import data from any sensor and deploy your model to almost any device. You maintain control of the data and firmware the whole time. The Edge Impulse Studio is an online platform that handles everything, including collecting data from your embedded sensors, labeling the data, performing any pre-processing calculations, and training machine learning models. This end-to-end project is called an impulse. You can then test your impulse on live data with a connected sensor. After, the studio will guide you through the process of creating firmware or a library that will run your impulse on any number of platforms. This includes your pre-processing code, trained neural network, and any anomaly detection code you may have so that you can perform inference locally without an internet connection. I'd like to show you how you can deploy your trained machine learning model to nearly any platform using the C++ library that you download from your Edge Impulse project. One question I often get is, once I have a trained machine learning model on my Edge Impulse project, how do I deploy that to a board that's not officially supported? This could be another dev board, or you could be making your own board with your own microcontroller or microprocessor. One option to do that is to deploy your model as a C++ library. I recommend going to docs.edgeimpulse.com, going to tutorials, and finding where it says deploying your model as a C++ library. This tutorial will walk you through the process that I'm about to show you and go a little bit more in depth behind some of the function calls that we're going to make. That being said, I'm going to walk you through the process right now. Let's start with an existing project. I'm going to go to studio.edgeimpulse.com/public/76063/latest. This is a public project that's been created with one of the data sets from Edge Impulse, and it involves moving a board around and figuring out the patterns that it's making and classifying those patterns. Note that you will need to clone this project, so click clone and create an account if you don't have one already. Once you create an account, it'll ask you the name for the cloned project and bring that into your account. I'm going to skip over to my account because I've already imported this project. You can see it right here, My Motion Project, and feel free to look around with the model testing. The model should be trained for you. You can see where we're moving the board around, wave, up, down, snake, and so on. It's not super accurate, which means we probably need more data, but that's okay for now. We're just focused on deploying this model to some sort of embedded device, or really any device right now. Let's go to deployment. Normally you would click one of these options for your particular board, but if your board is not supported, what we'll want to do is go to C++ library. This will download all the source code needed to perform inference along with your trained machine learning model, and it will run on your device so long as you have a C++ compiler and enough flash and RAM to run the model. Click on C++ library and scroll down. You can choose to leave Eon compiler on or off. If you leave it off, it means that the TensorFlow Lite for microcontrollers code will be interpreted, which means it's going to run a little slower and it will take up a little more RAM and flash. If we turn it on, it makes it a little more efficient by essentially compiling your model to C++ code. You can see the estimated utilization here based on an ARM Cortex M4F. I'm going to leave the Eon compiler on, and I'm going to click Build. We're going to wait a moment while that builds, and you should see that happening in the output here. And it should say that the C++ library has been built. Once done, go to your File Explorer and unzip that file that you just downloaded. I highly recommend going into this folder and poking around in the files here. You will see Edge Impulse SDK. This is all of the Edge Impulse library functions. If you go into here, go into classifier, and if you bring up EI run classifier.h, this is the file that you care about the most because it contains the public-facing functions that you will want to call in order to perform inference. The most important one you want is run classifier, so you can search for it. That's init when you are doing run classifier continuous, and here's run classifier. Feel free to look at this source code, but you don't particularly need to. You just need to know how to use this function. If we head back to docs, you can go to API reference, and you can see a section that's devoted to the C++ Inference SDK library. Here you will find a listing of all the macros, structs, global variables, and functions that you'll care about when running this library. If you go into functions, you will see that run classifier that I just talked about. You'll see that definition that I showed you, how to use it, and any parameters that are required. Note that if you are going to be running this on one of the non-supported boards, and I'll show you in just a moment, you will need to implement a set of functions so that it will run on your board. This is because every architecture, every platform is a little different. For example, if we want to print things to the console from within the library, such as debugging information, you will need to implement this EI_printf function. One example to do that is to have things print out over a serial port or a UART port. Or if you're on Linux, like a POSIX system or so forth, then you can use the built-in functions to print to the console. But you do need to define this function to make that happen, and you need to define all the ones that are shown here. If we go back to our folders, go into porting, you can see that these are platforms that are supported, which means the functions that I just showed you here, they have been defined in these files that are brought in when you compile your program. Since we're going to be working with a Raspberry Pi, I believe this is actually for the Pico, go into POSIX and go into EI classifier porting, bring that up, and you can see this is where those functions are indeed defined. Notice the weak attribute for some of these. That means you can override them in your own program if you need to. Generally speaking, the Edge Impulse library needs a way to sleep. You need to be able to get the system time in milliseconds as well as microseconds. It needs a way to print to the console, and you can see it using vprintf here to make that happen. If you're working with a microcontroller, this might be, say, print out over the serial port. And you need a way to allocate and deallocate memory. We won't go into these explicitly because they're already supported for Linux and many other microcontroller platforms, but know that if you are indeed trying to port to a system that's not listed here, you're going to have to write your own versions of those functions. Let's go back out to our top level directory, go into model parameters. These are the settings that are needed by the library. Model metadata.h contains a lot of the pound-defined macros that work as global constants. These are the ones that you'll probably care about. And this is where you can get information like your sampling frequency that's been set in the studio. And if you're working with images, your width, height, number of frames, and so on. For us, we're working with accelerometer data. In fact, it's a 3-axis accelerometer, which means there are 3 samples per frame or per instance that the accelerometer is sampled. We're working with 100 Hertz sampling rate. And because we get 200 3-axis samples per sample period, that gives us a total of 600 samples over a 2-second window. This DSP input frame size will be important later, and you can see how it's calculated by multiplying the sample count by the samples per frame. If I scroll over a little bit, you can see that calculation there. Model variables has your label names in a string array. You can see them listed here in alphabetical order. These are set in the studio, and this is auto-populated when you generate that C++ library. It also contains some settings for your DSP block. You should not need to change those. If you need to change them, you should change them in the studio and regenerate this library. Go back out and you will find TF-Lite model. This is the actual trained machine learning model. If you did not use the Eon compiler, you should see TF-Lite trained.h here, and that will contain a raw buffer of TensorFlow operations in byte form. If you are using the Eon compiler, which I did here, there should not be much in this .h, but some declarations of these functions. So let's go to the .cp, and you can see where a lot of these functions are indeed defined. And these are all the functions needed to perform inference after that DSP block. You should not have to change any of this code, but this is so you're aware of the source code that's inside this C++ library. If you're using CMake, you can copy this CMake lists, but I'm going to ignore it for now. We don't need the README. To make my model work, I just need these 3 folders. So I'm going to copy those. I'm going to go into my Raspberry Pi. I'm using SSHFS in order to mount the file system in Windows, but this would be the same as if you downloaded this model directly onto your Raspberry Pi. I've created a folder called Projects. I'm going to go into Edge Impulse, and I'm going to create a new folder. I'm going to call it My Motion Demo. In there, I'm going to paste those 3 folders that constitute the C++ SDK library. Note that Edge Impulse does have various ways you can automate this process by using their web API in order to build and download the C++ library directly using, say, command line scripting, Python, and so forth. I'm showing this to you the manual way so that you get an understanding of what's going on when we download that C++ library, but know that you can automate this function. Once that's done, let's create a new file. We're going to call this main.cpp. This is going to be our main application. You can do things with pure C, but it's a little tricky to set up. You can call a lot of the functions with C that are public facing in this SDK, but know that you still need a C++ compiler because a lot of the Edge Impulse and TF-Lite for microcontrollers code is all based in C++. So you can't get around having a C++ compiler. We're going to make a Makefile. And this is so that I can demonstrate how you include all of the necessary files, how you compile them, how you link them. This is just an example we're going to do on Linux to make it hopefully a little clearer how you use this library. I recommend using the Makefile as a starting point if you're using another development environment, something say Eclipse-based, and looking at what you need to include and using the GUI to include those if you're using, say, Eclipse. Here I've SSH'd into my Raspberry Pi. As I mentioned earlier, you will need a C and C++ compiler. To test that, let's try GCC. Good, GCC works. We'll try G++. That works as well. And Make. Good, all of those tools are installed. If you do not have those tools, you will need to install them on your system. You can get this to work on Windows, but this demonstration with Make works a lot better on Linux and Mac. To get it to work on Windows, you either need something like Cygwin or MinGW, and you can set up Make. You can likely also get it to work with Linux subsystem for Windows. I just haven't tried it yet. From here, let's open main.cpp. I'm going to copy in sections of code to save time here and explain what's going on. The first thing we're going to do is include our standard input-output so we can print stuff to the console. The only file you should need to include is this Edge Impulse SDK classifier EI run classifier. That's that first file I showed you when we were looking through the library. All of the public-facing functions should be in here, and any other structs or macros should be included in this file, so you don't need to include those separately. The next thing we need is to declare this callback function, which I'll talk about in a minute. We're going to need to define this, and it's something that gets passed into our classifier function, and that helps fill a buffer so that the classifier can do what it needs. Next, we are going to define our raw features, and I'm going to show you how to do this with a constant or static example so that you can see this in action. In reality, if you're trying to do this real time, you would have this buffer, and it probably does not need to be global like we're doing here, but you would just fill up this buffer with samples from your sensor. In this case, it might be a 3-axis accelerometer. Let me show you the example with a static set of features. And this is always a good thing to do to make sure inference is working the way you intend. Go to your project. Let's go to model testing. And we're going to pick something interesting here. I recommend not doing something that's 100% accurate because you want some variation among your classes. Let's go with this up-down motion. So say show classification, and it should come up with the classification results for that particular sample. And you can move this window around to find something interesting. So if I move it around, there we go. I like that second one. 0.25, 0.68, and 0.07 for snake, up, down, and wave. Those are the classifications. What we want is this set of raw features. So click copy to clipboard, and we're going to paste them where it says paste your raw features. It's going to be a very long array, but that's okay. Note that in this case, the way these features are defined is it's X, Y, Z for your first sample, and then X, Y, Z for your second sample, and so on until you get all 200 samples for your 3 axes. With that, we're going to start creating our main function. The operating system often needs these parameters, but if you're working with a microcontroller, you will probably find that they're not needed. We also need to define a few SDK unique variables. Signal T is used as a wrapper for holding our buffer. The result struct is used to hold the output of inference, and these error codes are used as a return value from inference to help us see if something went wrong. Next, we're going to calculate the size of the buffer, because we did not define the size of our array here. And we're going to check to make sure it is the correct length by comparing it to this macro. And this came from model_metadata.h, which we saw earlier. If they do not match, we'll get an error message and the whole program exits. Note that you will probably not need to do this if you are running things in a live environment, because what you're going to do is have an array that's one size, and it should be this size here of the DSP input frame size, and you just fill that array as you get values from your sensor, and then every time you filled the array, you call run classifier to perform inference. We need to define a callback function, which is used to fill the buffer that's used for preprocessing and inference. To do that, we set up this signal struct. We assign the total length, and it should be the same size as the DSP input frame size. And we're going to set this get data pointer to our function that we will define down below. This is the most important function that we need. This is the function that performs signal processing, which is the DSP block, followed by inference. When it's done, it returns that error code, which is stored in this res variable. All of the results from inference are stored in result. Notice that it takes in that signal struct, and this last parameter is debugging information. If you set it to true, it will print out all the debugging information as the function is being run using that EI printf function. So however that function is defined, it will print out using that. I usually like to check the return code to make sure everything is working, and you can also print out all of the timing from the DSP block, classification, and anomaly if necessary. We then print out the classification results. Object detection has a different structure for these results, hence we're using this preprocessor directive if we're using object detection. If you go into model parameters and open up that model metadata, you can see that object detection value being set here or not set. Since this is not a vision project and we're not doing object detection, that should be 0. So this part does not get run. If it is set to 1, you'll get bounding box information for your object detection. However, for us, what we care about is printing out these predictions. Notice that we loop through the number of labels. It prints out the categories that we saw in model variables.h, and there should be 4 of those. Remember that those will be in alphabetical order as set in the studio. And the results are stored in this classification array. The elements for your values line up with the elements of the strings for the labels in that array. Finally, if we do have the anomaly detection set, it will print out the anomaly prediction score that's stored in result.anomaly. Finally, we need to define that callback function I mentioned earlier, which is get signal data. That gets passed in to the run classifier. This is needed to page or buffer data out from our raw sensor buffer to the classifier functions buffer. This is useful if you can't fit all of your raw data in RAM at one time and you want to page chunks of it at a time for something like continuous classification. You don't know exactly when this function will be called, so just assume that any amount of your data will be requested up to that frame size constant we saw earlier, which is given here. And you can see that this output pointer is a buffer inside that run classifier, and all it's doing is just getting buffer from our input buffer, which in this case is our static array that we set up top. Now that we're done, save this file and feel free to exit out of there. At this point, you will want to open that Makefile. As I mentioned, Make is easy to play with inside of Linux, and it demonstrates what files and folders you might need to link to your project to get this whole program to compile. I recommend using this as a guide for linking to the SDK library in your own development environment. For example, in many Eclipse-based IDEs, you might have a GUI that you have to fiddle with in order to set the includes and sources for compilation and linking. This is just an easier written way to see what those files should be and what your includes should be. Let's start by taking our tool macros. We will set those for GCC and G++. We're going to name our output as app. That's what we're going to run, our executable. We're going to build that executable in the build path. And we have to give it the name of our main C++ source file. In this case, it's main.cpp, the one we just wrote. Next, we set our compiler flags for C. The interesting ones to note is this setting of the ndebug in order to disable that assert macro. And we need to enable special operations for TF-Lite. If you dig through some of the Edge Impulse code, you will find it relies on things like lambda functions, which means we need to use at least the C++ 14 standard. We also need to include math.h and standard C++.h. These might be a little different if you're working in a development environment for microcontrollers, so when you compile, I recommend looking for errors and tracking down any missing libraries or linkages. Here we note the locations of various source code for C and C++. Pay attention to the directories listed here. So for example, Edge Impulse SDK, CMSys, DSP, source, transform, functions, and then all of the C files in there. Same thing for the rest of the DSP functions. For C++, you will want everything in that TF-Lite model. You will want the Edge Impulse SDK, DSP, the KISS FFT library for doing fast Fourier transforms, DCT, memory. We need POSIX and MinGW32 if you're doing this in Windows. These two might be a little different for microcontroller boards. Remember what I mentioned about that porting library. So if you're doing something with, say, STM32, you will want to go into the SDK, look into porting, and you will say STM32Cube AI or the Sony Spresense board or Arduino, whatever your platform may be, you will want to replace these to include that particular porting set of functions. Or this is where you would define your own and point to them in this C++ sources variable. Edge Impulse can potentially support other machine learning platforms, but we're sticking with TensorFlow Lite for microcontrollers for now. To use TFLM, you'll need to add a flag and some additional sources that I've listed here. If your target has support for CMSIS neural networks, then you will want to include this whole section that has CMSIS NN libraries and enables some flags. This is important for some advanced ARM architectures that include those hardware accelerator functions. This will check if your architecture has it and include these files automatically, otherwise these are not included. Finally, we tell it to build all the source files. We compile them into object files. We include them and link them all together to build out our app application. And this is where we actually build the target for app. Note that if you're on Windows, it will create a build directory for you, and it will do the same on, say, Linux or Mac OS. It's just a slightly different command line tool. Finally, we have the clean target. So if we call make clean, it will delete all of those object files for us. It does keep the executable, so keep that in mind that you would need to delete that build folder if you really want to clean out everything. Let's save this. Let's go into our Raspberry Pi. And I'm going to go into that projects, Edge Impulse, My Motion demo folder. You can see all of the files we created here. I'm going to call make, because I have make installed and we're using Makefiles. If I do -J, that says to do this in an appropriate number of threads to make the compilation process faster. You will notice that there are a lot of files in this library, so compilation can take some time, especially the first time you do it. If you're porting to your own board, you will likely run into linking errors or compilation errors. Carefully read them, figure out what's missing. If it's something in that SDK library, you will probably need to include that folder either as a source or as a header file so that your compiler or your linker knows where to find it. Once it's done, you should see a build folder. We can go into that build folder. You should see your app and do ./app, and it should run your application. And pay very close attention to these predictions. Idle is 0, snake is 2.5, up down is 7.8, rounded, and wave is about 0.07. If we go back into our project, that should match what we saw in our inference output, which means inference is working from our C++ library. We included it manually and wrote an application to use it. I hope this helps you get started running the Edge Impulse inference code on just about any platform you want. I want to thank IoT Central for hosting this workshop. You can find more workshops at iotcentral.io, where this video will also be available on demand starting tomorrow. If you have any questions about Edge Impulse or you'd like to show us something you've built with Edge Machine Learning, please create a post at forum.edgeimpulse.com.